So, let us continue our study of ring homomorphisms. So, we have defined and looked at some important examples of ring homomorphisms. So, now I am going to start talking about associated things to ring homomorphism. So, let us start. So, what we will do now is talk about something called the kernel of a ring homomorphism. So, you all know from group theory, and when you learned about group homomorphisms, there is something called kernel of a group homomorphism. So, let us do that. Okay. So, let us look at kernel of a group homomorphism. So, and the definition is exactly the same. So, before that let me actually give you an exercise which we have essentially done in our calculations earlier. So, let us say phi from R to R prime is a ring homomorphism okay. So, here of course, I am not saying this, but R and R prime are two rings, R and R prime are two rings and phi is a homomorphism. Then if you simply look at phi, forget the multiplicative structure on R, in other words just look at the additive group of R and R prime. If you look at R prime, R to R prime as a function of the additive groups, this is a group homomorphism. Okay. So, if you go back to the previous video and just look at the relevant parts, you will see a proof of this. By definition, A plus B should go to phi of A plus B is phi of A plus phi of B, but the other properties will ensure that 0 will go to 0, phi of minus A is phi of minus phi A. Okay. So, this is not difficult to check. So, it is a group homomorphism. So, now recall, so this exercise for you to do. Okay. So, you have to do this. So, recall the kernel of a group homomorphism. What is the kernel of a group homomorphism? It is the set of elements that map to 0, right. Kernel is always the set of elements that map to 0. So, we use the same definition here. So, this is really a set theoretic object. So, we use the same definition for ring homomorphisms. So, the kernel of phi, so now this is just an aside. So, given phi from R to R prime a ring homomorphism, the kernel of phi which is denoted by ker phi is by definition the set of all elements of R, so that phi of A is 0. Okay. So, let us focus a little bit on what kind of element, what kind of subset this is. This is a subset of R, right. But because kernel is really defined using the notion of group homomorphism, it is more than a subset. In fact, kernel phi is a subgroup. So, I am going to write additive subgroup just to emphasize the fact that we are looking at the addition on R. So, additive subgroup of R comma plus. So, when I write R comma plus, I mean I am insisting to that I am looking at R as an additive group, forgetting the multiplication. So, it is an additive subgroup of R comma plus. This is exactly what we have done in group theory. So, there is, in other words, if 0 is in the kernel, that 0 is in the kernel is the first point. If A and B are in the kernel, A plus B is in the kernel, that follows from the definition. If A is in the kernel, minus A is in the kernel. What other properties of, now let us come back to ring theory, we are doing rings, not groups. So, what other properties does kernel have? Is kernel a subring? Think about it for a second. Is kernel a subring? It is not. Why not? It is not because remember a subring is a subset which is a ring by itself. In particular, it is supposed to contain 1, but can the kernel contain 1? No. Right, kernel does not contain 1, because what is phi of 1? By definition, phi of 1 is 1, and I am assuming as always that 1 is not 0 in R, in R prime. Okay, R prime, assume always all our rings are not 0. So, there are at least 2 elements, 1 and 0, they are distinct elements. So, 1 is not 0. So, kernel phi is not a subring. So, the analogy of with the kernel of a subgroup homomorphism being a subgroup does not carry over here, it is not a subring, but it does have nice properties. In particular, in addition to being an additive subgroup, it has the following property. Kernel phi has the following property. Kernel phi has the following property. So, if A is in the kernel, what I want to say is that it is closed under multiplication, but in a strong way. It is not just closed in the sense that multiplication product of 2 things in kernel is in the kernel, but product of something in the kernel by any group element is in the kernel. Okay. Why is this? So, why? This is very easy to check. So, what is, in order to check if something is in the kernel, we have to see if it is, its image is 0 or not. So, what is phi of R A? Phi of R A is by definition of a ring homomorphism is phi of R times phi of A. Now, R is an arbitrary group element. So, we do not know anything about phi of R, but we do know that A is in the kernel. So, phi of A is 0, right. Phi of R is something, but phi of A is 0, but phi of R times 0 is 0, because anything times 0 is 0. So, phi of R A is 0. So, that means R is in the kernel, sorry, R A is in the kernel. So, it has a very strong multiplicative closure property. Take anything in the kernel, take anything in the ring, not in the kernel, anything even outside the kernel, the product is in the kernel. So, kernel has the following properties. So, kernel has the following properties. It 1, it is an additive subgroup, of R plus, and 2, if A is in the kernel, R is in the ring, the product is in the kernel. Okay. Now, the we want to give a special name to subsets of a ring that have this property. So, kernel phi is a special case of that. So, kernel phi is an ideal Okay. So, what is an ideal? So, this is a very important word in ring theory. So, after defining rings and homomorphisms, the next important thing is this. So, I will formally write the definition, it is simply the properties 1 and 2. So, an ideal I of R is a subset of R satisfying. So, I am going to repeat exactly the conditions that I wrote. I is an additive subgroup of R plus. So, in particular it is not empty, remember 0 must be in I, and 2, if you take an arbitrary element of I and an arbitrary element of the ring, the product is also in I. Okay. So, the ideals are this, and kernels of homomorphisms are ideals. In fact, kernels or homomorphisms are exactly the ideal. So, in general any ideal can be realized as the kernel of a suitable ring homomorphism. So, the most important examples of ideals are the kernels of ring homomorphisms. Okay. So, so we started with the definition of a kernel of a ring homomorphism, and we noticed that it is not a subring, but it is what we now call an ideal. Okay. So, in order to understand more about ideals, let us look at some examples. Okay. So, the ring homomorphism that we looked at earlier, Z to Z mod 4 Z, what is the kernel of this? What is the kernel of this? So, I claim the kernel is all integers. Remember, kernel is a subset of the domain, in this case Z. So, all integers such that phi of n is the 0 element of Z mod 4 Z, which is 0 bar in our notation. So, this is precisely 4 Z, right. This is simply all multiples of 4. Okay. So, when does an element in Z go to 0 under this homomorphism? Remember, this map sends n to n bar, right. So, n bar must be 0. So, n bar must be 0, that means n must be a multiple of 4. So, kernel is exactly the multiples of 4. The other example that we looked at, let us say phi from Zx to Z. Okay. So, this is the substitution map. Substitution, remember phi 2 is what I think we looked at. So, here f x goes to f of 2. What is the kernel of this? Kernel of phi 2 is all polynomials in Z x such that f of 2 is 0. Okay. So, now I am going to tell you, ask you to recall something I talked about when I talked about division inside polynomial rings. So, recall, so in any ring R and any polynomial ring R x, if you fix alpha in R, let us say, so f x or g x in R x, we can divide g x by x minus alpha, right. Always divide that, because x minus alpha is a monic polynomial. So, we can divide g x by x minus alpha. The remainder is g of alpha, right. This I have proved. Remainder when you divide g x by x minus alpha is g of alpha. So, now if you apply this idea to our situation, in our case the remainder when we divide f x by x minus 2, now in our case x minus 2 is f of 2, right. And now, if f is in the kernel, now if f is in the kernel of phi 2, then f of 2 is 0, right. So, actually I will write it like this, f is in the kernel if and only if f of 2 is 0, because that is the definition of the kernel, f is in the kernel if and only if f of t is 0. That means, this happens if and only if the remainder upon division of f x by x minus 2 is 0, right, because f 2 is precisely the remainder when you divide f x by x minus 2. So, f 2 is 0 means the remainder upon division of f x by x minus 2 is 0. That means, f x is divisible by, right, that is what we say, when the remainder is 0 we say that is divisible. For example, when you divide 5 by 4 by 2, the remainder is 0, so we say 4 is divisible by 2. On the other hand, when you divide 5 by 2, the remainder is 1, so we say 5 is not divisible by 2. So, f x is divisible by x minus 2. So, kernel of phi 2 is precisely when if f x is divisible by x minus 2, that is another way of saying f x is a multiple of x minus 2, right. So, in other words, the upshot of all this is kernel phi is precisely set of all multiples of x minus 2. So, I can write it like this: kernel phi 2 is exactly x minus 2 times h x, where h x is any arbitrary polynomial of z x, right. Multiple of x minus 2 means x minus 2 times an arbitrary thing. So, that is how we describe the kernel of phi 2. So, kernels have this nice form. So, now I want to mention a nice observation. So, this is a small lemma. In the first example that we looked at above, kernel of the map from Z to Z mod 4 Z turned out to be multiples of 4. So, in other words, what I want to now say is that any ideal of Z has the form n z for some n greater than or equal to 0. So, any ideal of the ring of integers has the form n z. Remember what is n z? So, this is the set of all multiples of n. So, that is just a short convenient notation for writing all the multiples. So, n z stands for a n as a varies in z. So, I claim that every ideal has that form. So, this is a very nice result, right, because you can't have strange sets becoming ideals. So, every ideal is of this form. So, the proof is a standard proof using Euclidean division. So, let us quickly do this. So, let I be an ideal of Z. If I is equal to 0, remember I is an additive subgroup of Z. So, it must be non-empty. So, it must contain 0. If it is exactly 0, then I is 0 Z, right. So, we are done, right. So, we are done. So, please pay close attention to this. This is a very nice, simple, but an extremely important argument in ring theory, and this sort of thing comes up all the time. So, if I is simply just the 0 element, it is of the form 0 Z, right, because 0 times n as 0 times a as a varies is just 0. So, we are done. We are claiming that every ideal is of the form n z. If it is simply 0, then it is 0 z. So, assume I is not the set 0. In other words, I contains some other element. So, first of all, I claim that we can now assume, in fact, then I contains positive integers. If I contains something non-zero, it contains positive integers. That is because, very simple example. So, if for example, minus 10 let us say is in I, we know that I contains something non-zero. If it is positive, we are done. Suppose not, let us take a negative integer, but I is supposed to be a subgroup, right. So, minus of minus 10, which is 10, also belongs to I, right. So, I contains a positive integer. So, I contains some non-zero integers by assumption. If you happen to pick a positive number, you are done. Suppose you pick a negative number, you simply take its negative. So, I contains positive integers. So, that I hope is clear, right. So, I contains positive integers. Now, what I will do is let n be the smallest positive integer in I, Okay. I can always choose that, right, and I can have some positive integers. I cannot pick maybe the largest one, but I can always pick the smallest one. So, let n be that, let n be the smallest positive integer in I. Now, and then choose. Now, I claim that I is in fact n z. This n will do the job for us. I is n z. Why is this? So, choose, let first take care of positive integers. Let m be in I, m positive. By choice of n, by the choice of n, m is greater than or equal to n, right, because m is positive, n is positive, n was the smallest positive integer contained in I. So, m is at least 10. Now, divide m by n. So, what we can do is m is equal to n times q plus r, right. We can always divide m by n and we can write it like this. And what is the property of r? R is actually strictly between, sorry, r is either greater than or equal to at least 0 and strictly less than n, because we are dividing by n, the remainder will be strictly less than n. But now, notice an interesting thing, n is in I by choice, that means n q is in I, m is in I by also choice, right. That means m minus n q is in I, because n is in I by ideal property, n q is in I, m is in I by ideal property, again m minus n q is in I, but m minus n q is in R, is equal to R. So, that means R is in I. But now, we have a problem, because if R is positive, this leads to a contradiction. What is the contradiction? What is the contradiction? If R is positive, R is strictly less than n by choice of by the process of division. So, if R is positive, because we have then, because n is the smallest see, the contradiction is to the fact that n is the smallest positive integer in I. If R is positive, R is less than n, R is smaller than the smallest positive integer in I, which is certainly absurd. So, R must be 0, and hence m is divisible by n, which is another way of saying m is a multiple of n, right. So, what we have shown is that we have taken an arbitrary positive integer in I and showed that it is a multiple of n. Okay. Now, we want to say that every integer in I is a multiple of n. Now, on the other hand, if m is negative and m is in I, by the above argument, applied to minus m, right, if m is negative, minus m is positive, we know that minus m is a multiple of n, but then so is, right, minus m being a positive integer in I is a multiple of n, but hence obviously m is also, because minus m is n times something, m is n times minus of that thing. So, we conclude, in conclusion, every integer in I is a multiple of n, and we also need to show that also, since n is there in I, every multiple of n is also in I. Right, because I is an ideal, if n is there, every 2 times n is there, 3 times n is there, minus n is there, minus 2 times n is there. So, I is exactly equal to nz as required. So, this is a very beautiful argument which shows that every ideal in Z is of the form nz. So, we are going to talk more about generators of ideals later and talk about principal ideals. So, and at that point I will remind you, this says that, so this is just a preview of what I will do next. Every ideal in Z is principal. So, principal ideals are ideals generated by a single element. So, just to preview what I will do next, but I said that every ideal in Z is a principal ideal generated by a positive integer n, or of course, a 0 non-negative integer n I should say. So, I am going to stop this video here, but in the next video or in one of the next videos I will show that the same result holds for polynomial ring in one variable or a field. So, that I will do next. So, in this video we looked at kernels of homomorphisms, we looked at what properties those kernels have, and notice that they are examples of what we defined as ideals, and we looked at examples of ideals in various rings, and in particular we showed that every ideal in the ring of integers is of the form nz for a non-negative integer n. Thank you.